We have discussed the discriminant and we have found that if the discriminant is less than 0, we have the saddle point. Is neither maximum nor minimum. The discriminant t at the point, the critical point is bigger than 0, we say local extrema, but we have not distinguished it is local maxima and local minima. So here we can see if we are having dab is bigger than 0 and we are having xx, the second derivative also bigger than 0, we say is local minima at the point ab. And if the discriminant is bigger than 0 and the second derivative is equal to xx, we can take respect to x or respect to y. We can take f of xx or f of y. This is our choice. We look on the function which is easy to calculate. We use that one, yeah. But the result is same. Result is not going to change. We can take either one of this. So, but I'm writing here f of xx. You can take f of yy. So f of x ab is less than 0. We have local maxima at the point ab. Now I give you an example and I will explain further with the help of example. I give you the details of the method we have discussed with the help of example. We want to find the local extrema and saddle point if any of the function fxy is equal to x cube plus 3xy minus y cube. Second is a function of xy. So we have here function xy is equal to x cube plus 3xy minus y cube. Now we know that we need the critical point, number one. We find critical points. For critical points, as we said, our gradient is equal to 0. And then we have taken that mean f of x equal to 0, fy equal to 0. I find here f of x. My f of x is 3x squared plus 3y because my y is constant. Now f of y, I get here x is constant. We get here 3y minus 3y squared. 3x into 3, here we get 3x. And we are having here minus 3y squared. So we are having this one and we put this equal to 0 to calculate our extrema of the function. We put here f of x equal to 0. That's mean we have 3x squared plus 3y equal to 0. And we take f of y equal to 0. That's mean we have 3x minus 3y squared equal to 0. So this is my equation 1. This is my equation 2. These are nonlinear equations. Then we want to solve the nonlinear equation to find the value of x and y. I take from the first equation, I can say here my 3y is equal to minus 3x squared, and this implies y equal to minus x squared. We substitute the value of y equal to minus x squared in our equation 2. We get 3x minus x whole square. So get it 3x minus 3x power 4 equal to 0, and from this we can take 3x common and get here 1 minus x cube. So here we are having two roots, either x is equal to 0, I will say, and 1 minus x cube equal to 0. So one root I have here x equal to 0, and second root is the cubic equation. In this cubic equation we know we have only one real root. Or we expand this one, we get here 1 minus x into 1 plus x squared. Here the real roots is coming from 1 minus x equal to 0. This means x equal to 1. So the roots we get, the values of x, we are having here x equal to 0 and x equal to 1 because we are taking only real roots. Now we substitute this in equation 3 to get the value of y. When we put here x equal to 0, then our root is y equal to 0 from equation 3. When we take x equal to 1, y equal to minus 1. So I say here my critical points are 0, 0 and 1 and minus 1. So these are in the range of the function fxy. So here what's the range of this, domain of the function fxy, not the range. Domain of the function is, because the function we are having here is a polynomial function in x and polynomial function in y. So domain of the function is all values of x and y in xy plane. So because this is true for all values, from x is from minus infinity to plus infinity, y is from minus infinity to plus infinity. So it defined for all values. So we have these two values 0, 0 and 1, 1 also in domain of the function. So our critical points we're going to discover, the local extrema we're going to discuss at this point. So here our step 1 will be here to find the critical point. Then we are having the step 2. Our step 1. Our step 2 is to find the discriminant. Here step 2 is we discuss the discriminant of the function. And to discuss the discriminant of the function, we are going to use here our formula that we have developed, that our dxy is equal to f of xx xy into f of yy xy minus f of xy whole to power 2. Now we can just find here the second derivative. Here we have the first derivative, and I can write my second derivative, taking derivative of this one respect to x again. We get here f of xx is equal to 6x, y is constant. Then I take the derivative of this one with respect to y. We get here, this is x is constant, y is changing. We get here 3. And we get here f of y. F of y is x is constant, y is changing. I get here minus 6y. So this is my second derivative. So I use the second derivative, f of x, f of y, we get here 36y. And here f of xy whole square will be 9. So I am having here, I put the values here, the value of f of xx is equal to 6x. And here is minus 6y is minus 3 whole square. I recheck this one. So f of xx is 6x, f of y is minus 6y. Okay, it's fine. We just simplify this one and we can write here this is equal to minus 36 xy minus 9. So this is my discriminant. Now at this discriminant I take a critical point. My critical point, I take the critical point. This is my critical point is 0, 0. At 0, 0 when we find d0, 0 is equal to, when we define put value of x equal to 0, y equal to 0, the value of this one is minus 9, which is less than 0. So we say there is saddle point at the point 0, 0. So when we want to find this point in 3 dimension, this point will be like a, b, f of a, b. So when I find f of a is 0, b is 0, and then f of a, b, I put in a function, the value of x is 0, y is 0. This 0 plus 0 minus 0 will be equal to 0. So f of 0 is 0, 0 is equal to 0. So this is my origin and this is my saddle point. We say this point is 0, 0 and 0. And we can just have this saddle point. It's number 1. This here we can say, I can take as number 3. Third step, we have first step for critical points. Second step for discriminant, and then we discuss the local extrema. So I take the second critical point. This is my second critical point. Is a point 1 minus 1. This my a is equal to 1, b is equal to minus 1. We find the discriminant of this one at the point 1 minus 1. That's equal to 6 into minus 1 and minus 1 is 6 and minus 9. That give me 36 minus 9 and is equal to 27, and this is bigger than 0. So it means we having here local extrema. We can discuss here local extrema at the point because this is bigger than 0. Less than 0 was the saddle point. So I just discuss here local extrema, and I can have here the value of f of x I take. F of x at point 1 minus 1. My f of x is 6 into 1 equal to 6, bigger than 0. And when it's bigger than 0, this implies that we have local minima at the point 1 and minus 1. As I told you, we can take here the point f, we can take the derivative f of xx or f of yy. If you take here f of yy, you can see it here. And we just substitute the value of the f of y is equal to minus 1 again. We get here bigger than 0, the same result. The result is net changing. So if I want to find the values of the point, when I put here the point, this is 1, 1. To get the point, I find here my fxy is equal to x cube plus 3xy minus y cube. So the value of the function at the point 1, 1 is equal to 1 minus 3 minus 1, and we get here this is equal to minus 3. So if I want to write my critical point, we are having here the local extrema of the function. This is here. You can write here this is the 1 minus 1 and minus 3. This is the point we are having here, the local extrema at this point. So that's the result of this one. We're having only one local minima and at the point minus 1, minus 1.